forum, so I'm just here to facilitate and I guess try to prime the conversation. I guess this is the first one we've had here, so I can sort of make the format. Yeah, the topic is speed versus accuracy. For example, extreme points are languages like Fortran. Pretty much the rules say, well, when it comes down to speed versus accuracy, the compiler can do whatever it needs for speed. And at the other extreme is, say, Java, which said, well, here, we're even going to give you trig functions that behave identically across different platforms. So just to get things started, some examples here are like, should in Julia, is 0 times anything equal to 0 and for floating point arithmetic or not? I believe that's not true. 0 times is not a number is not a number. For some people, that's when they really want 0 times not a number is not a number. For other people, it can be a significant speed improvement if you let the compiler have the flexibility to do the substitution. Reassociating just addition. I have an example tomorrow. 12x factor 12x improvement just by giving the compiler latitude to reassociation. Another one coming down the pike, a fuse multiply add. Some hardware has operation this thing called fuse multiply add, where you take a multiplication and an addition and jam them into a single operation. The good thing is it runs about the same speed as a single multiplication or addition. You get a 2-for-1 deal on performance. And the answer is almost always more accurate than what you would have gotten doing the multiplication and addition separately. But the answer is different. So it's going to annoy people who were expecting exactly getting the same result all the time. And there's a few corner cases where it can throw people for a surprise. That was complex arithmetic. Turns out complex division, you can't do it using the rules you learned in grade school. In fact, the current Julia library does complex division using the fancier approach, doing at least double precision complex division. But there's also cases, Julia doesn't do the fancy version for complex multiplication for double precision. Some people may need that. And likewise, absolute value, that's a tricky one to get right, complex arithmetic. But if you know your complex numbers are reasonably small, like, oh, maybe they're all in a unit circle, there are faster ways to do it. And then another one, fans of fairly low precision arithmetic, for like single precision division. There's a way to do it faster on some platforms. If you're allowed to round the last bit, not quite perfectly, the nearest. And finally, I guess one that gets a thorn in my side as a former compiler person is precise exceptions. If you give the compiler latitude to throw an exception earlier than where the error actually occurred, there's some significant speed ups in the game. For example, suppose that you have a loop, and somewhere in the loop, the compiler can prove that an exception is going to be thrown. If it can throw it before you enter the loop, there's a lot of loop optimizations that can be done then. The only other thing I'm going to say is prior art. Here's what I've seen as prior art. People are pricing, I've only seen some languages. One is C99 has pragmas to control the environment, whether, for example, fuse to multiply add is enabled or not, or whether complex numbers have limited range or not. Another form that controls sort of stuff is compiler switches. Look at the Intel compiler. There are gobs of switches, whole sections of the man page devoted to these switches. I can't figure them all out. And finally, there's things like that. There's an earlier talk. There's lexical scoping methods like the at in bounds macro. And you look at like C#. There's for unsafe code. There's an unsafe lexical scope marker. So that said, I mean, do people have, I guess, other examples or opinions on what they really need?
So I'd like to advertise, just in case anyone here ever finds this information useful, I'd like to advertise probably the most infuriating problem of this kind that we have. which is integer division and remainder. Because we would actually be fine with the hardware behavior, at least on x86, of division in exceptional cases, like dividing by 0. But unfortunately, in LLVM, it's undefined. And LLVM has a rather interesting sense of humor about undefined behavior. And if it detects that you might be doing one, it will go ahead and substitute anything at all that it likes as the answer.
But only when it can prove it. So it can do division by 0, and you will get hardware behavior.
Sometimes.
But only when it can prove that
That's
it's doing
right.
division by 0.
So it's very so it depends on what optimizations LLVM does to the code. So it's very unpredictable.
Yeah, so it seems fine, and then you use a constant in your division expression, and LLVM gives you a random answer.
So if there isn't right, so we would be happy with something if we could just tell it, please just emit the x86 divide instruction here, no matter what. That would be a big improvement, but we can't do that yet. So this is a huge problem.
This is something to bring to the LLVM people.
Yeah.
Maybe another division operator or something, or flag it.
Yeah, there have been a couple of threads about this on the LLVM list, but they have not been loud enough. And
But doesn't Swift do the right thing?
What's it do?
Swift now does the thing we
doesn't
want to
accept
do, and so we're assuming that they must internally have a branch of LLVM. Patches it broken.
That's very possible. So I hope we get that eventually.
You can only get that on the Mac.
Yeah.
The LLVM, yeah, for those that aren't privy to LLVM's internals, the LLVM basically, if they find something that has undefined behavior according to their standards, then they treat that as they can do anything they want. This is so bad that the C++ committee is actually looking back at C++ undefined behaviors and seeing how many they can close, all because of LLVM.
Because I guess in the past, a lot of C compilers would say things are undefined, but in practice, you always get the same thing for a particular compiler. At least.
Right, you got something that's so implementation defined.
Right, but in LLVM, it's not even that. It just does whatever it feels like in each case.
One thing I wanted to, elicit opinions about is so integers and integer overflow check. So currently we just overflow, and that's what C and Fortran do, and it's fast, and it's exactly what the integer operations on the machine do. Doing what Python does, where you auto promote to big ints, is just not workable because you can't make the performance reasonable enough. But doing overflow checking would be possible. Art, you might have good insight into whether that would be a total performance nightmare, or if the optimizers could figure out most of the time that there's not going to be an overflow, so it would eliminate the checking.
It costs you a branch, is what it comes down to.
Right.
Yeah, it's pretty bad.
And what do you do if it overflows? Like, what's the...
You would get an exception.
Okay.
So the default, an alternative would be to have the default behavior be if you have addition that overflows, you get an error.
Yeah.
Unless you use a special wrapping addition operation.
MATLAB does saturation. That's like
That's the worst thing I could possibly do.
Another question from Modi. So on overflow, one of the things that I've had debates about overflow with many people that I've introduced Julia to, and everybody's a bit surprised, especially coming from Java or Python particularly. My experience is that usually the numbers that you're working with are always bounded by your domain. And so, if you're working, I work for the work that I do in finance, the price of a stock is always between 1 and 1,000. And if you're using integers tends to fluctuate. It's very, I can't say a situation where I would worry about overflow. My numbers have to be within the domain, and if they aren't, and it blows up, then it blows up, and there's a very serious bug in my input data. So I've never felt the need of actually checking for overflow in sort of most real-world situations that I have, because the domain defines what your numbers are going to be. It's very unlikely that you will have numbers which do cause an overflow.
In image processing, where the pixels might be UINT8s because that's what the file format encodes them as, there are a lot of operations you can do that would cause an overflow for sure.
Sorry, I misspoke when I said just the branch. It turns off almost all your optimizations get shut down. You can't reassociate integer arithmetic anymore.
Yeah, so I mean, my naive hope was that there might be some way to, coax the compiler into realizing that, like, in this loop, you never actually have to check bounds. You can just do this one branch up top.
You have to add overflow.
Yeah. But does anybody else have situations where, it was like really problematic to have, in actual code that you were using in some situation, it was really problematic that integers overflowed? I mean, C has bugs with this all the time, but my impression is that in C, the overflow, it's the combination of overflow and lack of bounds checking. Right, you have an overflow and you end up with like a negative index and it allows you to access memory that you shouldn't have been accessing.
The overflow is undefined behavior. C spec, the many programmers rely upon it. In fact, there's a paper at MIT how it opens up security holes.
Yeah. Unsigned overflow is defined just fine.
Yes.
Signed overflow.
Right.
I had a bug once like this. I was dealing with a really large mesh, and the mesh comes in as a list of vertices, and there was a lot of vertices, and I was performing some integer multiplication and it overflowed. But I mean, that was me writing bad code and not testing my input data correctly.
Yeah, I mean, your language has a responsibility to try to help you not write bad code or discover bad completely written code if you did write it.
Just have to resort to the classic vice of adding a compiler switch.
That's not bad.
Which is, it's not bad.
Is there any way we can just expose just the flags that are being set? I was going to ask that. Like, I mean, there is a flag for overflow, right, that is being set by the CPU. Can we not see that?
Is it always set?
I don't know. I have no idea.
It's always set, yes.
It's set, and it's promptly clear. It's reset by the next operation.
Right.
Yeah.
Yeah, and so that's actually an interesting point, because LVM will give you that flag, and so we don't actually necessarily need to check it and get the code to throw exception. We can just look at it. That's an interesting idea.
Yeah. So like, I never interact with anything that's ever going to overflow, so it's just like not worth it to me. Like the only use case for me for integers is like an index into something that's well defined, like a user ID. And so it's totally indifferent to me. So I have no desire to spend that cost, but it seems like if you know that this is a risk, you can just instrument your code with this, and only in the cases where you think it's a risk, check it.
Facebook user IDs do overflow 32-bit counters, though, so that's...
Yeah, there's no 32-bit counters around.
Along the point of, if you're allowed to reorder the exceptions, you can combine a bunch of them, check it at the end. Still doesn't let you reorder quite as much, but...
Oh, you mean like at the end of a loop?
Yeah.
You just have a boolean that's like looking.
Accumulate a flag and say an overflow happened sometime in the past piece of code in some way. That's kind of interesting.
That's what I believe.
Oh, by the way. That's an interesting idea.
It's like the global variables.
Like floating point exception flags. Yeah, that would be a nice way to remove floating point exceptions as well.
Yeah.
Don't want to big operation and then save the flag, like, or the flag, and then at the end of whatever periodic,
At the end of it, that would be a cool feature. Yeah, that's worth it.
Maybe not even every loop, but like when you finish executing your script, it says, warning, this script had a overflow in it that is not marked as expected.
I don't know, IDL destroys. That's totally useless. I mean, it just, they always say this, overflow, and you're like, okay, somewhere in the 10,000 lines. So, I don't know, the compiler switch seems like the best bet. I mean, they just get an exception saying, here it is.
Yeah. Right. But then you can turn on the compiler.
Yeah, maybe a combination of a warning, if it's cheap enough, and the compiler switch that will actually tell you if you want to again where it was.
Well, there's also the problem that there's code that like intends to overflow.
Yes,
That's true. I mean, there's the classic, find the midpoint between the high and low value by adding them and then right shifting. It works
Well, another one that keeps me up at night is just converting integers, which is right now we don't check. It's really the only conversion we don't check. And that doesn't seem so great, but for some reason truncating integers is so commonly done. It's so useful that it's, the idea of going through and finding everywhere that relies on that is just really daunting.
I'm more in favor of that. Does anybody
But
else
that
feel
seems like
like
a
we
good
should
change,
be
but-
throwing errors if you try to truncate a 32-bit integer to an 8-bit integer and then 5 bits that are success? You think so?
I mean, we should have a truncating one.
Yeah, but you can do that with like,
Yeah.
an AND operation.
I mean, it seems like is that kind of analogous to like if you try to convert a float that's not an integer like to an integer and you get an inexact error.
Right.
It seems like it's the same kind of thing.
That's
why we like it.
We
Yeah,
should
yeah.
maybe do that. But it's also one of those things where you're like, you kind of know what it's going to do, and people use write code where they expect to get the last 8 bits by converting to a UNA.
Yeah.
So,
But it seems like if you like, I feel like that's like idiomatic old school C code.
It is.
Like because like
yes. So the
based
question
on
is that a
rules.
bad habit or is it a good habit?
But it seems like anding it with
Yeah.
OXFF before you do that truncation, like and making it explicit that you're masking out the rightmost 8 bits. Like it seems like it's good to make that explicit by anding FF before you truncate.
Yeah, not much sort of how to get a boolean, treating 0 as a false.
Convert sort of exists as this like lossless conversion, like it's most of the time
it's lossless except for when it's not.
Yeah.
That's kind of why it's like a little sketchy that it sometimes just throws data away.
Yeah, you sort of expect it to result in like a different type representing the same thing, so it makes sense for it to.
Yeah.
I mean, and if those semantics were like set as a rule, it'd be like that would be a nice thing to be able to rely on.
Yes,
but it might not be.
If you convert something, it should not lose information about the thing that you converted.
Yeah, that seems like a good change. Yeah.
This does roll back towards the overflow discussion, though. If you were adding two 32-bit numbers and storing in a 32-bit location, we may be promoting. I don't remember if that changed.
I think that would have
addition
changed
you
too.
would convert to 64, and then because the storage location is 32,
Yeah, so
you get
those changes
overflow.
actually go together because then you wouldn't be able to get sort of reliable 32-bit integer operations because you get errors, some percentage of the time. So those changes go together, I think.
Yes, the highly unpopular, adding two UN8s and getting an N64 behavior is probably going to go.
That maybe was just a mistake.
It seems reasonable at the time.
So is the plan now just to type C?
I think so,
Yeah, to do.
Ironically, that's what we originally did, and then we went through a huge hassle to change it to the other thing. And change it back. But did people think changing that is a good idea? I feel like that's like highly popular.
Yes.
But
It is a good idea.
I think it's a very good idea.
I mean, I think I'm in favor of it, but I also recognize that it's going to be a dangerous transition, right?
Yeah.
So I mean, it will break a lot of code that is currently working.
Yeah.
I guess one of the questions I have, not knowing a lot about the SIMD, for example, though, is can we almost not keep the current promote to int 64 first before doing operations if we also want to really sort of use the full width of the SIMD?
Yeah, that could be an issue. Yeah, that's very possible.
So then, if that's the case, and I suspect that there's a lot of interest in more widespread use of SIMD in the long run, then almost for consistency, it seems like we have to say uint8 plus uint8 equals uint8 or something.
Because the SIMD-like operation of just operating on arrays, that is what we do. We keep the type the same for arrays already. So
Right.
Yeah, one of the several reasons to change it.
So I think a good way to think about it is to work backwards from what you do with arrays.
Right.
So figure out what you want arrays to do, and then figure out the scalar case based on that.
Yeah. So for reductions, we'll have to declare the output type, right, so that you would accumulate specifically to an int64 if you are wanting to sum a whole dimensional array, for example.
Yes, because if you start summing int 8s,
Yeah.
you would get int 8.
Yeah.
Which just seems useless, but I mean, for summing, just specifically for summing, that's not what you want, probably.
Unless you're doing like a checksum of a binary, you know, like an overlap checksum or something.
Right, but I don't think that's what people expect sum to do. Yeah. It is in the name, but.
One of the things that happened recently was this power operation. I thought that power has very weird edge cases which don't make sense when you agree.
Yeah, power is such a nightmare.
That's horrible, yeah.
Issue 7233. So I did a bit of sleuthing on this. I thought that like C99 defines power and they just made up the edge cases from what I can tell, and like even they don't make any pretense of justifying it mathematically. And so the IEEE coding point standard, the most recent one from 2008, introduced two other power functions to circumvent the fact that power is just weirdly defined by edge cases. So they chose to be backward compatible but just have the functions. So that's the kind of thing that can happen in this situation, right? And yeah, so currently if you do like the caret operator, so A caret B just calls power, but I'm wondering if we should call power R or something like that. Otherwise that's a lot of time.
What are the edge cases you're talking about?
Excuse me?
Can you give an example of one of the edge cases?
-1 to the in.
So that's the very place where there's the branch coded power, right? So
Yes,
it's always
exactly.
all problems in IEEE are ultimately related to branch code.
Yes, yes. What does that mean? Like, you know, for the vast majority of people, like, nobody ever wants to compute that. But, like, you know, for the purpose of actually, you know, everything that we've implemented the power function, that we actually have to say that, you know, that we have some justification for the behavior.
Well, to me, it has more to do with bugs. It's like if you accidentally did -1 to the int because of the bug, what's going to happen?
Right.
And you could get a misleading wrong answer.
Right.
Probably there should be a -1 plus 0 and a -1 minus 0 if you should split the branch cut, maybe.
Yeah, so I mean, this goes back to the earlier point I was making about like, you know, like when I was working in Fortran code, like by far the best thing to do to debug in Fortran code is to pass like you know tap coding point exception and just find out like when the thing is throwing in for an error div 0. Like that turns out to be one of the most useful cases because most of the time you're computing some kind of matrix or you know some large array of things, and those things should be finite value, and if there's infinite values, then usually that's the best problem in the computation. So that's the kind of thing that I find very useful for most people.
So maybe the most useful thing we could do is have a mode where you like, you know, run Julia in paranoid mode and everything is kind of slow, but any questionable behavior will throw an error.
I'd also be in favor of blocks, like so you have some sort of instruction to say, you know, for this bit of code, I want to run this methods. Because often it is very, you know, you find often that you want different specific behavior for certain blocks. Right. You don't need it for the whole program.
So lexically scoped or dynamically scoped, because that's always an issue.
Depending on my phone.
Yeah. Because then, you know, the difference, I don't know if it's clear to everybody, but lexically scoped means it's only the code that's like literally in this block of, if the operation was in this, you know, piece of the file that you can see right here, then the change applies to it. Dynamically scoped means anything that's called from here has the different behavior. And the problem with the dynamically scoped, the good thing is that, you know, you're doing operations. So let's say you call some function and you decided to turn on overflow checking. You know, does the sum function, if it overflows, throw an error because you called sum or not? Basically, is the question. Because the sum is doing the actual addition operation, but the addition is an addition that you explicitly wrote. So for some, chances are, yeah, you want to throw an overflow. But if you change the behavior of things, then, you know, and you call some code that has, you know, relies on overflow, for example, because it does the add and then shift right trick, it's going to throw an error when it shouldn't. So I don't know. I don't think there's a correct answer.
Can you talk about dynamic scoping in Julia in general? Like, is there a general facility for dynamic scoping? I guess it shows up sometimes because there's like rounding modes for floating point.
Yeah, so
but it doesn't seem to show up very much,
it's
right?
really awkward, which initially I thought was just a missing feature, but now I think it may be a feature that it's awkward. So the way you do dynamic scope is you use this thing called the task local storage, which I don't even know if we export, but there's a thing called task local storage.
It's exported.
Okay, and you basically just get a dictionary that's local to your task, and you can stick things in it and take them around it, and that's it. That's how you can implement dynamically scope.
Well, at inbounds is dynamically scoped, right?
No. It's classically scoped.
Okay.
So if you call something that does, or it indexes into an array, that will still check. The things that the indexing you actually do in the current block of code will not be checked.
I thought we have a subarray issue pending on that. Okay.
So I mean that may be one approach to handle it is have some way for particular pieces of functionality to register that they want to check the caller's setting for the flag and inherit it. Right? Like so some would inherit the overflow checking behavior and
that seems confusing.
Yes, it does.
Yeah, all these things just get complicated.
Yeah.
I don't think it would be too terrible if you had to annotate, or if you can annotate like where you expect overflow and then have a parallel, right? Because I mean, expecting usually overflow doesn't occur, and the problem is that just adding it by default is too slow. But when you actually, in the 1% of cases where you actually do want to overflow, like just add overflow, put that a name, and then having the parallel mode that is 2 or 3x, maybe 4x as slow as the usual mode, but actually throws an error, I don't think that will be too terrible. And not necessarily just overflow. I mean, Hal mentioned floating point exceptions. I think floating point exceptions could just do the same thing.
Maybe garbage collection. That'd be a useful thing.
Throw an error on garbage collection?
Not throw an error, but it's been something that it would be useful. I wish there would be some kind of macro that you can annotate a block of code and it will come back and tell you which lines actually did memory allocation, because I tend to do that manually whenever I'm trying to optimize something.
Yeah.
Tell you about it.
Yeah.
And then it was.
So profile view tries to essentially will examine the backtrace to see if it sees signs that the garbage collector has been collected. So it doesn't mark the lines that allocate. It only marks lines that cause garbage collection, and those two are coupled. But you can see really strange things where like the allocation of a 1-2 tuple, takes more time, appears to take more time and causes garbage collection compared to a mega, byte array or something like that. And that's just because of when the garbage collector gets triggered, basically. So it's not perfect. But
Yeah, I think I misspoke. I meant allocation, lines that do allocation, not lines that do garbage collection. That's right.
That wouldn't be too terrible to add, like a flag that just every time you do allocation, just tracks how much allocation you do and catches the backtrace.
That would be super useful.
Yeah,
I spent a bunch of hours.
There's one allocation function.
actually, I bet Leah would like that, right? Because I mean, a lot of the typing errors in people's, type instability in people's code result in array allocation. So it'd be a great way of catching.
Collecting a full backtrace for every single allocation is going to be really slow, though. I mean, you'd have to do some kind of sampling, probably, like every 100th allocation or something, maybe.
I mean, that
might be okay. That's true.
Yeah. Or also, the same kind of thing we were talking about having like a decorator, not a decorator, like being able to wrap that block of code and say, hey, like when you run this, I want as output. I mean, we have the allocated macro that you can put on like a single expression, right, and it'll tell you. But it'd be nice if you could do the allocated on a block of code and not just get how much that whole block did, but you get like each line how much it is allocated. But like because like most of the time you don't need it. You don't need it like just when the code is running in general. You need it when you say my code is slow and I'm trying to fix it. So what I do is I put like a time on one line, and I see how much did that allocate, and then like I move it to the next line, and then move it to the next. So I do that like kind of line by line, which is there's maybe a better way to do that already with the tools that exist, but like kind of automating that process would be really
Jeff always has secret tools. He uncomments some line somewhere in the C code where he compiles everything, and then it tells you all the things you need to know.
And then every now and then there are people who like to discover these things and then document them. That's very, very disappointing.
I admit, I actually use V-tune amplifier to pop up the assembly code for you when I'm trying to figure out where time's going.
That was your first pull request.
Yes.
That was a really awesome thing. How can you step through the assembly in that?
Yeah, you can see it line by line. Right now there's an off by one source line issue. I have a patch for it that I'm not sure what to do with.
Is it a patch for V-tune or for?
It's a patch for LLVM to make it put the lines off the other direction, so that when the amplifier reads it, it'll compensate for the bug. It's sort of embarrassing. I don't know.
So the bug is actually in V-tune?
Yeah, the bug's in the V-tune.
Okay.
So I guess too embarrassed to put it in as a PR. I'll put it up as a GIST.
There's one thing that would be nice to have further down the line is also like something like one all, just like convert warnings to errors. I'm saying you got one error.
I mean, I don't want to have too many options, right?
Yeah. But I'm also, I really don't like warnings. I think you really have to commit to just like, this is either a problem or it's not. Like, you really got to minimize warnings,
Yeah, we've been doing a poor job of that with ambiguities.
And deprecation.
Well, that's one of the things. Yeah, I mean, they're just a very small number of things that give warnings. You have to keep that under control.
Very small number of things that give a lot of warnings.
Yes.
Yeah, the deprecation of the warnings definitely helpful because particularly early on when the language is changing, it's helping find out, change the code as the versions have been incrementing.
Yeah.
Yeah. So those are very helpful. Yeah.
I like that they're fairly specific too. They tell you exactly what you should change the code to.
Yes, they've been very helpful.
And I've actually really come around to the idea of replacing the ambiguity warnings with runtime errors when you invoke an ambiguous case. Like initially that seemed like a bad idea to me, but I just completely changed my mind, and it actually seems like kind of an awesome idea. So
I would be happy with that.
Because
basically once a week waking up and finding the data isn't broken, I would definitely like to see less ambiguity warnings.
Yeah. Because then you could just define all the ambiguities you want, just go crazy with it. And then if someone actually hits one of those cases, they have to say, oh yeah, I have to decide here what I actually want to do. Do I want the answer to be an image or an array?
What is it?
Your code?
Does it just pick one?
Picks one and prints a warning.
Yeah. So that's not so great. Getting a runtime error would be really cool.
Yeah, I think I wouldn't mind that.
Yeah.
Even if I can't fix the ambiguity right there because I don't know the package, I can at least explicitly select one or use invoke select.
Yeah, because that's bad. It's like a boilerplate generator. It's like, okay, now I have to generate or type out 100 definitions that are just totally boring, just disquiet the warnings.
Things
and that's
that never happen.
Yeah. So you shouldn't have to have that kind of boilerplate. So.
Yeah, it's like, are you really gonna call an SI unit with a math constant?
Right.
I mean, you might, and you should get an error. But
and if you do, then you've got to clarify what you want to have happen. So I think that would be great. Yeah.
Yeah, that's actually a good point. I think there's a huge problem with ambiguity warnings of things that just don't make sense, but theoretically could be ambiguous.
Yes. Yeah.
And then people just define it to throw an error anyway.
Yeah. So we should embrace the ambiguity, allow as many ambiguous definitions as people want. It would be great.
It's actually a huge problem for writing a generic linear algebra stuff because you would like to run things for abstract array, but abstract array comes with so many things. Yeah.
I don't want to do it. Yeah. It's
one thing if you get five.
Yeah. It's I don't want to do this.
I want to throw something out. A new ternary operator. Use one of those Unicode symbols for FMA.
that's one I wanted to raise back. Yeah, the FMA issue. Should it be the default, or should it be something?
Well, we should make a new create a symbol explicitly for it. Called the Unicode.
How about calling it FMA? FMA function. If you want it, you call it. Is that not good enough?
For some people, it kind of obscures the code, and code's like Python.
So will LLVM not generate FMAs by default unless you pass some
can't.
on safe math flag or something?
Right.
Yeah.
FMA. That's the
Fuse multiply add. So what's the danger with FMAs? Why is it not allowed?
I mean, it gives you different answers.
Because you get different results than.
Isn't it usually correct? More correct.
More correct.
Usually more correct. There's two examples where it actually will trip you up. There's like the quadratic form.
I've seen weird examples where you thought you were for sure going to take like the square root of a positive number, like you were doing norms or something, and you go into the complex world, because of the FMA. There's some really weird things that just happen.
So would it be reasonable to default to saying okay to FMAs and then have some way of indicating that you really don't want one?
That's what a lot of compilers have, right? They just turn off generating FMAs.
Yeah, what would you prefer, Adam? On the spot.
My general life observation is that there's more discussion about these topics than sort of bugs that have actually really happened. So I don't know is the short answer.
Fair enough.
Yeah, code that depends on the precision of your floating point type might get tripped up by that.
But I feel like that's rare. Usually you want more precision.
Not necessarily. I mean, like what if...
I feel like if you know you care about the precision of your floating point type, so like you know enough about what your code should actually do, that you are more capable of annotating it than somebody who just like wants it fast.
But I also think, given that it's if anything more accurate, then that's kind of an argument in favor.
Yeah, it's the weird behavior, right? I mean, trips up people and then you get issues.
You'll find those out when you get the weird behavior.
There's a related
and then you spend, several hours on Google trying to figure out what the hell's going on.
We just run everything in double and then see what.
We don't have double.
But we could.
Run everything in half precision and see what breaks.
But it does tie to something in the sense that at the moment, I think, as I understand it, Julia is very strict about the, it doesn't sort of C will use like float 80 or whatever the native precision if you write that and then truncate it only when you explicitly cast. Whereas, as I understand it, Julia at each operation explicitly rounds. I'm not sure if that's true, but that's seemed to be my experience as it was in whereas an FMA, if you have implicit FMAs, that is the counter. That is the one exception to that behavior.
We don't do anything to make sure that every operation is rounded, but I guess usually the instructions we generate are not using the 80-bit registers, I believe.
Correct.
So you're not going to get that. But
so there was actually one bug which was found recently, the complex test failing on like i386.
Yeah.
Yes.
And it actually failed because on i386 there's none of the SIMD registers that do like the double precision floating point arithmetic. So the more precise answer was rounded differently than the less precise answer that we were getting with double precision floating point. Even though it was on i386, which has like targeting i386 and thus generating floating point 387.
We does have some 80-bit registers would behave differently than the SIMD register.
That's right. That was the problem. Like somebody used the target i386.
It's all these distro build.
Right. All the distro builds want to target like minimum, so they don't use any SC instructions. Hence, they got 80-bit arithmetic, which actually broke one of the tests, which was assuming that we wanted to. And so there's one case where we already are not doing the most precise thing we could, and getting appropriate speed.
So Wikipedia just reminded me of the Kahan example, where you could take x squared minus y squared and x can equal y, and the result will be negative with FMA. So these are the things that annoy people somehow.
What is it, x squared?
You take x squared minus y squared, apparently the result could be even negative.
Yeah, I think it appears in Wilkinson's book as well.
Those examples aren't necessarily just toy theory examples. You have, for example, in computational geometry, a lot of situations where you just have a predicate function. And if something is negative, you say, okay, it's inside this geometry object. If it's positive, it's not. And that getting that to be a robust and correct is non-trivial. And I think most people just use extended precision, but a lot of people don't because it's too slow.
You put the burden on annotation. People know what they're doing, and people don't.
How do you feel about AD registers? Are they dead as a doornail?
Yeah, they're vestigial hardware that we continue to support, but it's with fewer transistors, I think is the answer.
Alan, do you know any examples where if you reassociate matrix multiply, you get something
You could just do simple addition examples, which is sort of a special case of matrix multiply, right? It's dot product of all one. You could always make weird things happen if you take enough numbers or you have enough different size numbers.
So what's the best case where you want the compiler to go in and put in an FMA, but if I'm writing code and I don't know about FMAs, but I really want the compiler to do this for me, what are the arguments for allowing FMA to happen behind the scenes?
Basically performance factor 2 in this case.
Well, but can you talk about a specific problem or something? Something that
they're all over.
Matrix multiply, which is at the root of most dense linear algebra, is all FMA, and the computers love to do the LinPack benchmark, whether anyone actually needs these things or not. The LinPack benchmark is so ingrained in the culture that every computer manufacturer wants, or every chip
That's the
manufacturer.
only reason FMAs really exist in the hardware.
I have a feeling it's more benchmark than real applications, but yeah.
It's a ring. It's mathematically it's a ring. Rings are popular for a reason.
You're not letting my joke go. You're right. Yeah.
But you might argue that the dense linear algebra is a thing that's going to be written by a specialized group of people who should maybe be expected to know about FMA and use it. And I mean, if there's cases where you don't want it, then maybe it would be better just to have an FMA function that the specialists should call, and everyone else gets the semantics that they would expect.
You could argue the other side, which is almost equally good, which is go for it, try to get the speed, and if you run into a problem, deal with it. Right?
Yeah. From the compiler standpoint, what's the granularity that you can switch this on and off? Is it
instruction level?
Yeah.
Okay.
Yeah. You just say don't generate FMA.
It's a different instruction.
So you could have a meta operator that says do or do not use FMA for this particular instruction, plus question mark or
I think
something.
the Intel C compiler has a flag, if I'm not.
Most compilers have a flag to turn it on globally, but you can always so in LLVM every floating point add or floating point multiplier, you can annotate fast.
Yeah, that's
fmal fast,
right.
And then if it sees a fast mul and fast add next to each other, and the hardware has FMA, it will do the appropriate thing and emit the FMA.
The if-fast calls for a lot of instructions.
Yes.
See, at the programmer level, C99 is basically a pragma that turns on or off whether you can do a floating point contraction.
But this is something that would happen in the compiler optimization thing. It's not something that you would.
No, you can also do it explicitly.
Sorry?
I mean, the way you would do it explicitly, I think LLVM actually has an FMA intrinsic, but usually a lot of LLVM optimizations are on pattern matching. So as long as you know what pattern LLVM is matching against, you just put that in, and you're pretty much guaranteed to get the optimization.
But I mean, it wouldn't necessarily match up one for one with what your source code looks like an addition followed by a multiplication.
Yeah, well, I mean, so in the case of the optimization, the compiler builds a graph and sees if it can move it across the loads and stores. Because arithmetic is pretty nice in that you can move it around a bit. The only problem being floating point flags. If you check for them, then it can't move across that. So it knows where the boundaries are that you can move across, and then it'll do if you annotate it correctly, it will do the optimizations even if it's not directly followed the multiplication by now.
I'm thinking it might detect cases where you wouldn't even realize that
that
could happen behind the scenes.
Most
so
like most of the cases that it would do, you probably didn't think that it was a fuse multiply out.
I don't know if this is a conscious design decision about the language. One of the things I really like about it is that you can start with not that much sophistication and get a lot out of it, but then the more sophistication you have, you can go in and do all this stuff. Given these the x squared minus y squared thing sounds pretty bad, but as someone who doesn't know it, as someone who's on the less sophisticated end, if I had that behavior, I'd be a little bit freaked out. So it sounds like this being something that you can then go turn like annotation or something like that is nicer, because then.
That's a problem with floating point arithmetic in general. I feel like if you whenever you have a hard cutoff, whether it's 0 or anything else, comparing.
I mean, x squared minus y squared, where x is equal to y, giving you something less than 0 is pretty horrible. I mean, that's worse than normal horrible.
Well, the other, again, there's a flip side, like 2x2 determinants, where you get them fairly accurately, so you can decide whether a 2x2 matrix is singular, which is also a big base case. What I'm saying is it's backwards. Now the fuse multiply add works very well to help you in that situation. So it's a trade-off.
I think the question is whether this should be opt-in or opt-out.
Right. I think that's what.
And I think another question is if there's a subclass of places where fuse multiply adds can be automatically added safely. I don't know if that's probably not a case, because otherwise the compilers would already do it. But
well, wouldn't you because most of the people are going to be porting their code to Julia, right? And so if they get this behavior that's different than what they're trying to match against, then I think that's bad, right? So it should be opt-in, I would feel.
But it depends on what you're porting from, because you could be porting from a compiler. I mean, that is generating FAA.
Are there languages that automatically apply to fuse multiply add?
So certainly MATLAB, it'll depend on the machine. MATLAB doesn't dictate, your machine does.
But you have to leave it at that. Thank you for moderating, and thank you all for participating. So just take a really short 1 or 2 minute break.